So yeah, this is the live interaction for week 4 classes. So good afternoon everybody, and it's perfectly 3 p.m. So I guess we will wait for 5 minutes, and if nobody joins then I'll definitely continue my session. So yeah, so let's wait for the 5 minutes and then we can see what can be done. So we're waiting for 5 minutes. In the meantime, you can see this screen that I'm presenting. Hi Kartika, we'll start at 305. 35. Am I audible to you? You can write in the chat box if you yeah. Okay. So did you go through the week 4 classes? Week 4. Huh? Okay, no problem. It's 302. We'll start at 335. Okay, good. Let's wait for other people to join. If somebody joins, I'll continue, because I think most of the people watch the YouTube uploaded video instead of joining a live session. So people are more interested in, I guess, seeing the solutions of the assignment questions, because 5 or 6 questions I always have from the assignment. So yeah, let's see. I'm waiting for 2 3 more minutes, then we can continue. So I guess not many people will join today. So I'll first give you a flashback of week 4 classes, the combined PDF, and then some of the basic notes, and then we can start the assignment questions. So basically, if we go through the week 4 classes, before going to the week 4 classes, there is something basic thing that we should know. Only see the yellow part which is marked or highlighted. Let me see if my mic is open. Yeah, it is open. So okay. So in the week 4 classes, Professor Tomer has mainly talked about interaction of electromagnetic waves with the matter, and the concept of radiation detectors. So how do you detect the radiation, in what mode you should detect the radiation, what kind of materials are good, what is attenuation coefficient, and etc. So first of all, we should know that how does the electromagnetic radiation interact with the matter. So if we talk about the radiation, so you see this plot, there could be ionization or molecular vibration. So if we see it from the perspective of increasing energy, we can see there is microwave, there is infrared wave, there is visible, there is ultraviolet region. But when there is an X-ray, there could be ionization, there could be longer wavelength X-ray, and there could be Compton scattering and photoionization. What are these terms? So the different parts of the electromagnetic spectrum have very different effects upon interaction with matter. Starting with low frequency radio waves, the human body is quite transparent. Just a minute, somebody is joined. Hello Arumugam ji. So I've just started. So I'm just giving a quick introduction, and then I'll talk about the week 4 classes, what Professor Tomar has taught, and then we can discuss the assignment. So basically I was talking about different kind of radiation and their interaction with matter. So you just see the highlighted part, that if we increase the energy, the different parts of electromagnetic spectrum have very different effect upon interaction with matter. So starting with low frequency radio waves, the human body is quite transparent, and as you move upward towards microwave to infrared to visible and then ultraviolet and then X-ray, you become transparent again because most of the mechanism of absorptions are gone. You then absorb only a small fraction of radiation, but the absorption involves the more violent ionization events. Example, this. Each of portion of the electromagnetic spectrum has quantum energies appropriate for the excitation of certain types of physical processes. The energy levels for all the physical process at the atomic and molecular levels are quantized. And if there are no available quantized energy levels with spacings which match the quantum energy of the incident radiation, then the material will be transparent to that radiation and it will pass through. If it is not responding, it will be transparent. I am trying to tell you that in the week 4 classes, Professor Tomar has talked about how does electromagnetic radiation interact with matter, and then the concept of radiation detector, like how do you detect the radiation, what kind of materials are there, what are scintillator, and different modes. So I'm just trying to give you a basic introduction regarding that. So there could be ionizing radiation, there could be non-ionizing radiation. So there could be a microwave radiation, there could be infrared interaction, there could be visible light interaction, there could be UV interaction, and then there could be X-ray interaction. We should know what are X-ray. So what happens in X-ray? X-ray photon energies are far above the ionization energies of the atoms. Okay. So since the quantum energies of X-ray photons are much too high to be absorbed in the electron transition between states for most of the atoms, they can interact with the electron only by knocking it completely out of the atom. That is, all X-rays are classified as ionizing radiation. This can occur by giving all the energy to an electron or by giving part of the energy to the photon, which is Compton scattering or ionizing. At sufficiently high energy, the X-ray photon can create an electron-positron pair. Now, let me tell you why it is important. Now, going to the lecture of Professor Tomar. What he has taught that electromagnetic radiation could be gamma rays, could be X-rays, or could be Bremsstrahlung. So what are these? Gamma rays are the de-excitation of the excited nucleus, and X-rays are the de-excitation of excited atoms, and Bremsstrahlung is a radiation emitted by accelerating charged particles. Now there are three kinds of processes which are taking place, as I have already shown you here. There could be Compton scattering, there could be pair production, there could be a photoelectric effect. So ionization and excitation is what? There is no primary ionization, ionization is completely by the secondary ionization, etc, etc. So what is photoelectric effect? Photon interacts with the absorber atom and disappears completely. An electron is emitted from the bound shells. Okay, so what are the characteristics? Full energy deposition of the gamma ray, highest probability, and post photoelectric effect phenomenon are photoelectron, X-rays, and Auger electrons. It is Auger electrons which are the post photoelectric phenomenon. So going further, he talked about a plot that what are the probability of photoelectric effect, lower the photon energy, higher the Z atomic number, higher the probability of photoelectric effect, and how does the full energy decomposition of the gamma ray happens, why the gamma rays are important and how they are full energy and what is the mode of them. Then there is Compton scattering that he's talked about, where the photons interact with free or loosely bound electrons in the medium, and it follows a conservation of energy and momentum. So this is the second process, and the third process is pair production. In pair production, what happens? Photon disappears in the Coulomb field of the nucleus, and pair of electron and positron is produced, whose energy is EE plus and EE minus equal to h nu minus 1.02 mega electron volt. And you can see the probability plot is like this. And further going to the plots, you should go through this plot which he has taught. Then what is attenuation? So attenuation is how deep can the ray can penetrate, and how after going deep, what is the most? See, it is exponentially decreasing. These kind of questions are there in the assignment. I'm just giving you a flashback of the class in the initial 20-25 minutes. So what is there are two types of attenuation coefficient: linear and mass. One is density dependent and one is density independent. So remember it. Then comes the interaction of neutrons with matter. Neutrons are neutral particles. They have no Coulombic interaction. There could be slow neutrons whose energy is less than 0.5 electron volt. For them, elastic scattering is not important. And fast neutrons, for which elastic collisions is important. And nuclear reactions are like this. Okay, now going further, he talked about the range of neutrons, go through them. Then in the next lecture, he introduced the radiation detector, the concept of a radiation detector. So how does you collect the ion pairs, and how does they help in radiation detection? Now there could be two mode of radiation detection. One could be the current mode and one could be the pulse mode, okay, or the voltage mode, you can say. So going further, this is a plottable diagram of a radiation detecting system where there is a detector and there are these parts, and we get the pulse height with respect to the dn by dv, and there are different portions which you should go through in the literature in the lectures. Then how does the energy resolution is there? Higher the number of ion pairs charge carriers and better is the energy resolution. Resolution means how much how sensitive you can separate or how broader you can do it. Okay, now going further, for the detection efficiency, there is this formula, counts per seconds. Please go through the formula. And then he talked about counting statistics. Then he talked about dead time. Go through it in how much time two separate events, so that they are recorded as two separate pulses. So time required to process a pulse is dead time. N equal to true count, M equal to observed count rate, and tau is the system dead time. So go through the lectures. Then there are method of dead time measurement. What are these? And then in the next lecture, he talked about different kind of detectors. There could be gas field detector. There are certain terms for a gas field detector, which is electric field gradient, drift velocity, etc., etc. There are various regions. When you increase the dose rate, the recombination regions also changes and the intensity also changes, but the nature remains the same. And then there is an ionization chamber where the collection of primary ion pairs happens. Energy required to form one ion pair is W, and number of ion pairs N equal to E by W. Remember, this W is the ionization energy. Now there could be pulse height, and there are certain filled gases which could be helium, argon, and methane. Why do we use this noble gas? Please go through it. Then there are certain application of the ionization chamber. Then there is a third part which is proportional counter, where each primary electron creates an avalanche. Then there is a secondary ionization. Then there is a multiplication in number of the ion pairs. Now proportional counters it is generally cylindrical in nature and most widely used for alpha beta counting and low energy X-rays. Neutron counters are filled with BF3 or 3 helium. Now there is flow proportional counter, then except many concepts are there. The other one is Geiger-Müller counter. It is one of the oldest radiation detector. Advantage is it is simple, low cost, and easy operation. Okay, space charge due to positive ions near to the anode effects are there mainly, and this is a figure schematic of a Geiger-Müller counter. Then there is some basic things that irrespective of the type of energy of radiation, Geiger-Müller tube gives the same pulse height, and then there are certain filled gases. What are they? Remember them. Then there is multiple pulsing. Application of Geiger-Müller counter, simple counting of the beta active samples, and laboratory experiments. Then in the last second lecture, he talked about scintillation detectors. What are the requirements of a good scintillator, which could be high scintillation efficiency, transparent to lambda of its own emission, short fluorescence decay time, refractive index of glass, and manufacturable in large size. Organic scintillators could be organic molecules with pi electron structure, pure organic crystals, example anthracene and stilbene. There are certain molecular phenomena which takes place. Liquid organic scintillator include topo and PPO. Solvent could be toluene and xylene and dioxin. And then there is wavelength shifter, which is pop-up, which is 1,4-2,5 phenyl oxazolyl benzene. Then there are organic scintillators, which is gross counting, alpha liquid scintillation counting, 100% detection efficiency, beta scintillation counting is less than 100. Then there are plastic scintillators, which have fast fluorescence decay, typical resolving time, and positron annihilation lifetime. Spectroscopy generally looks into it. Then there are inorganic scintillators, energy states of a crystal lattice, there is valence band, conduction band, and example is NAI. The electron may occupy an activator site whose ascent to the ground state is forbidden, radiation less between the excited and the ground state. And then this is NAI-TI detector, which is advantage have NAI-TL detector is most widely used scintillator since 1950s. Its disadvantage is it is hygroscopic, and there are the certain properties. Then he talked about the energy resolution of it, and then detection efficiency of it. Then this is a photograph, and then he talked about LABR3, and in the last class he talked about, which is the most important, is semiconductor detector. What happens when a high energy beam falls on a semiconductor, how does the electron get excited, example silicon, and what are n-type semiconductor? They are electron rich dipped with pentavalent impurity, example phosphorus and antimony. P-type are electron deficient doped with trivalent impurity, example boron and aluminium. Then there could be forward biasing and reverse biasing. In the forward biasing there is large leakage current, and in the reverse biasing there is a small leakage current. This N and P only happens when you provide a bias. Then there could be HPGE, which is high purity germanium detector with impurity concentration of 10 raised to the power 10 atoms per centimeter cube. And just a minute. N plus contact by lithium evaporation onto the lab surface, P plus contact by metal to semiconductor surface barrier junction, and needs to be kept at 77 Kelvin during operation to reduce the leakage current. Okay, then there is HPG detector energy resolution, and then there are certain properties of it. Then there is gamma ray spectroscopy, and what is comparison of HPG and NAI-TI for gamma ray spectroscopy. Then there are silicon based detectors, which are generally used for X-ray spectroscopy or XRF. Advantages are they are less prominent X-ray escape peak than germanium, and then there are surface barrier silicon detector where the ion are implanted over the silicon detectors. Go through the lecture and I think you will be able to understand. So in short, we can say, I know most of the things must have gone through above your head if you have not gone through the lectures, but I just wanted to at least make you familiar with the terms detection, ionization, Compton effect, what are these. So at least now you know there is something like this exists. So if I'll explain your assignment and later on you go with my recording or the video or the lectures, you may be able to understand. So now I'm starting the assignment. So this is the week 4 classes based assignment on the basis of week 4 classes. So let's go to the first question. The first question is saying which process results in the full energy deposition of gamma ray photon. Just a minute, somebody is trying to join. Okay. Hello Mani, am I audible to you? Mani, can you hear me? Arumugam ji, can you hear me? Kartika, can you hear me? Mani, I'm talking to you. You can type in the chat box if you cannot speak. Am I audible to you? Kartika, am I audible to you? Arumugam ji, am I audible to you? Should I start the assignment discussion? Okay, great. So now the first question is saying which process results in a full energy deposition of. Okay, great. So which process results in the full energy deposition of gamma ray photon in the detector? And the options are photoelectric effect, Compton scattering, pair production, and Rayleigh scattering. Can anybody of you answer this question? I am giving you 2 minutes. If you can answer, very well. If you cannot answer, then I will explain again. Just let me just show you the question. Yeah. The question is saying that which process results in the full energy deposition of gamma ray photon in the detector, and the options are photoelectric effect, Compton scattering, pair production, or Rayleigh scattering. And you can write in the chat box if you know the answer. If you don't know, it's okay, I will explain. Do you know the answer? Kartika, Mani, Arumugam ji, anybody? Photo. Okay, Mani is saying photo. Kartika, what about you? Okay, no problem. So right now I explained you that how many kind of interaction of radiations are there with the matter, and how many kinds of electromagnetic waves are there depending on their ionization energies. Now they are saying, the question is saying which process results in the full energy deposition of gamma ray photon in the detector. Let's see. So what Professor Tomar has taught, if we talk about three rays, specifically gamma rays, X-rays, and Bremsstrahl lung, so there could be ionization and there could be excitation. There are three processes which are taking place. The processes are photoelectric effect, Compton scattering, and pair production. Now let's see each of them one by one. What happens in a photoelectric effect? Photon interacts with absorber atom and disappears completely. The question is saying which process results in the full energy deposition of gamma ray photon. Now read the definition again. Photon interacts with absorber atom and disappears completely, and electron is emitted from the bound shell, and the formula is E is equals to h nu minus VE. So the properties are, there is full energy deposition of the gamma ray. Incident gamma ray is there falling on an atom, and then there is a photoelectron which is coming out. The predominant mode of interaction at low energy and highest probability. So the answer is right. Mani answer is right. Photoelectric effect is the right answer. There are certain post photoelectric phenomena which take place, which are photoelectron, X-rays, and Auger electrons. Now what are Compton scattering and pair production we should know. In Compton scattering, what happens? Photon interacts with free or loosely bound electrons in the medium, and it follows conservation of energy and momentum, and then depending on the angle the h nu varies. So there is in Compton edge which comes into the picture. For details you can see the lecture. And then the third one is pair production. What happens in a pair production? Photon disappears in the Coulomb field of the nucleus. Pair of electron and positron is produced. So there is full energy deposition in single double photon escape peaks. So the question was which process results in the full energy deposition of gamma ray photon in the detector. We had four options. Professor Tomar has explained that in a photoelectric effect full energy deposition of the gamma ray happens. So the right answer is what? Photoelectric effect. You can see there is this plot also, which if you see the attenuation versus the photon energy shows the probability of the three dominant interaction processes in the matter as a function of photon energy, which are Compton scattering, photoelectric effect, and pair production. So this figure displays the discontinuity at the binding energy of the electrons in the atom. The decrease of the probability of the photoelectric effect when the energy increases. The dominance of Compton scattering is at the medium energy, and the dominance of pair production is at the highest photon energy. So basically, the full energy deposition of the gamma ray happens in the photoelectric effect. So the right answer is photoelectric effect. Good, Mani. So I hope you have gone through the lecture. Now let's go to the second question. The second question is saying Which radiation or radiations follow exponential decrease in transmitted intensity as a function of thickness while passing through a medium? The the options are alpha particles, beta particles, gamma rays, and protons. And you have 2 minutes if you can answer this question. Anybody of you can answer this question? Acha Kartika, first question is clear to you? Did you understand something or should I explain in detail? You have to attend some classes. Now you know at least there is something like photoelectric effect, Compton scattering, pair production, and how does it happens, how is full energy decomposition happening, and then there is a plot of photon energy. Okay, great. Now if you go to the lecture, you may be able to understand if you're not from the same background, but at least now you know the terms, which is my duty as being a TA. So the second question is, which radiations follow exponential decrease in transmitted intensity as a function of thickness while passing through a medium, and the options are alpha particles, beta particles, gamma rays, or protons. And you have 2 minutes to answer this question. You can answer this till 3:28. If you can answer it pretty well, if not, no problem. So Mani is saying alpha, very great. Why do you think, Mani, it is alpha particles? Acha, do you know the penetration length of alpha particles, the strength of alpha particles? Like which amongst the alpha, beta, and gamma penetrate the most? Okay, great. So if they are penetrating more, do you think they could be? Yeah. So there could be more exponential decrease if you are saying so. Kartika, what is your point? Arumugam ji, what do you think? What is the right answer? Yes, yes, I know. That's why I'm waiting. Arumugam ji, can you mute it? Can you mute the?
Okay, sir. Sorry.
So the question is, which radiations follow the exponential decrease in transmitted intensity as a function of thickness while passing through a medium? And the options are alpha, beta, gamma, or protons. Okay, now let's go to the answer directly. Let's go to the answer. We know the characteristic of all these three particles. Now have a look over them. First is alpha, then there is beta, then there is gamma. We know alpha particles are doubly charged helium nuclei, as we can see here. Beta are Ds and gamma is this. Mass number is 400 and the charge is 2 plus on alpha, 1 minus on beta, and gamma are neutral. One is a helium nucleus, one is a pure electron, and one is a electromagnetic radiation. Okay, now the question is saying something. Which radiation? Now remember it. Which radiation is there? The answer you yourself know. Still, I'll go forward. These two are not radiations in terms like what is the radiation you have to understand. Now, as far as the penetrating power is concerned, Mani, the alpha particles are minimal. Okay, it will not penetrate the skin. The beta are short and the gamma are deep. You can see here there is a paper, there is aluminum, and there is lead. Alpha cannot even penetrate a paper. Beta can penetrate a paper, but it cannot penetrate an aluminum sheet, and gamma can penetrate more, but there is a reduction. So we can know the answer could be the gamma and the protons. Now let's see. This is the answer. What happens in a gamma ray if you plot it intensity versus thickness? Intensity of the parallel gamma ray as a function of absorber thickness is that ki gamma ray intensity decreases exponentially as the thickness of the absorber increases, and the formula is I equal to I naught e raised to the power minus mu x, where I is the intensity at distance x and mu is the absorption constant and x is the thickness. So as the thickness is increasing, the intensity is decreasing, and that is also exponentially. You can see the plot is exponential. So the answer is gamma rays. Do you understand it, Mani? Mani, did you understand the answer? Mani, Arumugam ji, Kartika, did you understand the answer?
Yes, sir, I understand, sir.
Okay, great. Others, you can write in the chat box. Money, be active. Okay, great. Makes sense. Now let's go to the third question. The third question is saying which of the following gases is used as a fill gas in a proportional counter for counting neutrons? This is why I was giving you a flashback. If you have not seen the classes, I just now told you the detectors could be of many types, how what are the basic features of a radiation detector, and now there is a type of detector which is gas fill detector. Now the question is saying that which of the following gases is used as a fill gas in a proportional counter for counting neutrons. So there are certain parts of a gas fill detector. There is one part is which is the proportional counter. Okay, so in this proportional counter, which gas is filled? Argon, argon with methane, xenon, or helium? Anybody of you know the answer, you can write in the chat box. If you don't know, I'll explain. Money, do you know the answer of this? Kartika is saying option 2, argon with 10% methane. I guess it is right. It is good. Good. I just showed you. I think you have gone through the classes. What about you, Money? Okay, no problem. I am telling you the answer. So, when we were discussing a gas field detector, there are certain parameters. There is electric field gradient, there is drift velocity, and the typical collection time. Now, as the strength of the radiation increases, the nature remains the same, but the intensity increases, which is VR versus V naught. You have to go through the lecture. Now, there are certain parts. So, the second part is the ionization chamber, but they are asking a proportional counter. So, if we talk about the ionization chamber, there is a collection of primary ion pairs, and the energy required to one ion pair is W electron volt. Okay, so the number of ion pairs will be E by W, where W is more than the ionization energy. Example, the fill gases are helium, argon, and methane, where W is 31.7, 25.9, and 29. So then there is pulsite and all. You have to go through it. Now let's come to the question. The question is saying higher the V naught than IC, each primary electron creates an avalanche. Then there is a secondary ionization and multiplication of number of ion pairs. The total number of ion pairs is m cross n. Okay, so for proportional counter, m is constant. So stringent requirements on the purity of gases is required. Arumugam ji, have a look. Okay, so because this is constant, it has to be maintained here. So a stringent requirement of purity of gases is required, and it is generally P10, which is 90% argon plus 10% methane. No trace gases of such having high electron affinity is required. Example, water and H2O. Why methane? You have to go through it. Then how this photoelectron from the cathode and spurious pulses happen. So the right answer is 90% argon and 10% methane. Okay, P10. The question was saying which of the following gases is used as a fill gas and a proportional counter for counting neutron. In a gas field detector, we have a part which is a proportional counter. In a proportional counter, we have stringent requirement on the purity of gases, which is 90% argon and 10% methane. Okay, so good, Kartika, you told the right answer. I guess you have gone through this class. Did you understand it? Kartika, Arumugamji, and Mani. This is a question from your assignment, I guess.
Yes, sir.
Okay,
Oh, yes, sir. This question is of a month. Yes, sir. Thank you.
okay. Now let's go next. Okay, there are certain properties of the proportional counter. There could be xenon or krypton filled proportional counter, which are good for XRD, and etc. And generally, a cylindrical shape is preferred, which I have already told in the beginning. And then there are neutron counters, which are filled by BF3 and 3 helium. This is a heavy atom of helium. Okay. Now the question number 4, which detector can not distinguish between alpha, beta and gamma radiation? Ionization chamber, proportional counter, Giga-Muller counter, or the gas flow proportional counter? It is 3:35. You have 2 minutes to tell me the answer. Oh my god, the answer is visible already. Do you know the answer? Kartika, Mani. Anybody want to type something? Okay. So the answer is gigamolar counter. What happens in a gigamolar counter? It is one of the simplest and oldest radiation detection. So it is low cost, but it is has multiple avalanches due to the each primary electron. So it has a multiplication factor of 10 raised to the power 6 to 8. So there is a cathode and then there is an anode wire. So the gigamolar counter cannot be used to distinguish alpha, beta, gamma radiations. Okay. Now let's go to the next questions. Kartika, did you understand it? Mani, Kartika, Aramugamji. This is a question from your assignment only. Did you understand the answer? Mani, are you there? Okay, no problem. Now let's go through this question. The question is saying which detector is most suited for X-ray spectroscopy, and the option are NaITL, HPGE, silicon lithium mixture, or xenon filled proportional counter. And I've given you a hint what is a semiconductor detector. These were developed in 1960. They are based on silicon and germanium. In a semiconductor, we know when there is a radiation falling, then this electron hole pairs happen and the electron get excited and go to the conduction band, and the band gap is nearly 1 electron volt, 1 to 1.25. Silicon has nearly this, germanium has nearly this, and in the n-type semiconductor they are electron rich and they are doped with pentavalent impurity, example phosphorus and antimony. In a p-type semiconductor they are electron deficient, they are generally boron and aluminum, etc. So the question is saying which detector is most suited for X-ray spectroscopy. Let me have a look if it is recording even or not. Yeah, it is recording. Anybody of you know the answer? Anyway, the answer is visible. The answer is silicon lithium mixture. It is clearly mentioned here. Only one option is there which is having silicon. Now why there is a lithium mixture? Now let's see what happens. What happens here, in a high purity germanium detector, it is a p-type germanium crystal and it need to be kept at 77 Kelvin. So it cannot be operated due to the problem of a leakage current. Now in a silicon based conductor, the question was which is most suited for X-ray spectroscopy. It is the most suited for X-ray spectroscopy because even the less prominent X-ray escape the peak than germanium. Now they have greater transparency of silicon for high energy gamma rays and less escape of electron from detector surface in case of beta counting, and typical energy resolution of 5.9 electron volt in a silicon lithium detector, which is 150 electron volt, which is pretty good. Therefore the correct answer is silicon lithium. Okay, let's go to the next question now. Semiconductor detectors are operated in reverse bias mode. The reason is to reduce charge collection time, to reduce operating voltage, to reduce trapping of electron and holes, or to reduce the leakage current. I just now told you, if you have not gone through the classes, what are semiconductor detectors. We know what are semiconductors now. There are two types of semiconductor, N type and P type. What happens when the electromagnetic radiation falls on the valence band? Now it excites, and there is an electron and hole pair which gets created, and the electron gets excited and goes to the conduction band. And excitation of electron from valence band to conduction band gives the formation of electron and hole pair. Okay, so they are high energy resolution and they have pretty fast timing. So the question is saying this semiconductor is generally operating in a reverse bias mode. Why is it so? To reduce the charge collection time, to reduce the operating voltage, to reduce the trapping of electron and holes, or to reduce the leakage current. Now what is the meaning of reverse bias? Reverse bias is what? Now when you are combining a N and P type junction, no, there is an intrinsic region which is taking place here until and unless there is no biasing. Now when you are giving a biasing, no, when you are giving a biasing, the forward bias is when you are connecting the negative terminal to the N side and the positive terminal to the P side. The reverse biasing is when you are connecting the positive terminal to the electron, I mean the N side, and the negative terminal to the P side. This is a reverse biasing. Now in a forward biasing there could be a large leakage current, okay, and in reverse biasing there could be small leakage current. Anybody of you can tell me why? And the options are: semiconductor detectors are operated in reverse bias mode. The options are to reduce charge collection time, to reduce operating voltage, to reduce the trapping of electron and holes, or to reduce the leakage current. Now can anybody of you tell me the answer? The answer is written on the screen. I have already told you what a semiconductor detector, how does an electron hole pair takes place, what is forward biasing, what is reverse biasing. Now why the semiconductor detectors are generally operated in a reverse bias mode? What is the right option? Anybody of you can tell me? Write in the chat box. Or speak up. Anumugam ji, do you know the answer? Mani, Kartika, anybody?
Option A, sir, reduce charging collection time.
To reduce the charge collection time. Okay, you're saying that it is
Yes.
operating in a reverse bias mode. So you tell me how will it reduce the charge collection time if it is in a reverse bias mode? In fact, it will increase the charge collection time. No. Okay, the answer was written on the screen. It is to reduce the leakage current. In a reverse biasing, there are small leakage current. So the right answer is to reduce the leakage current. Okay. Yes, good. Kartika and Mani told the right answer. Good. Now let's go to the next question. You can go through the explanation I have already written here. So if you have not understood it, why is it there in a reverse mode and what happens in a forward biasing mode, you can go through this. I'll upload it in the drive. Now question number 7. Question number 7 is saying HPGE detector has excellent energy resolution due to a small size, a small W value, high Z or high purity of the crystal. What are HPGE detectors? In case you have not attended the classes, they are high purity germanium detector. They are highly pure. Their concentration is generally less than 10 raised to the power 10 atoms per centimeter cube. In a p-type germanium crystal, N plus contact is by lithium evaporation onto the left surface, and P plus contact is by metal to semiconductor surface barrier junction. Now there is a problem. They need to be kept at 77 Kelvin liquid nitrogen during operation due to in order to reduce the leakage current. Now the question is saying HPGE, which is high purity germanium detector, they have excellent energy resolution. What is energy resolution? I have already explained you in the beginning. Now the question is saying this कि HPGE detector has excellent energy resolution due to a small size, a small W value, high Z or high purity of the crystal. Anybody of you know the answer? Mani is saying pure, high purity of the crystal. Okay. So they are generally pure in nature. But what is W? I told you. So what happens? Let's see. So energy resolution is what? They have very good energy resolution. For 1 mega electron volt of gamma ray, the N equal to E by W is nearly this. Okay, and experimental values are nearly this. There comes a factor which is Fano factor comes into the picture, which is the observed variance over the Poisson predicted variance. Now what are these? You have to go through the lecture. But let me tell you, they are very good energy resolution. Now what happens? What happens? HPG detection efficiency is lower than NAITL, and this is why. The efficiency decreases with E gamma. If the only the detection efficiency would have been a reason, then the high purity of a crystal could be the answer. But let's see now. So what is it saying? High purity germanium detectors have excellent energy resolution due to their small size and reduced electronic noise. HPG detectors are widely used in nuclear spectroscopy such as neutron activation analysis due to their high resolution. HPG detectors have an energy resolution of about 0.15% at 662 kilo electron volt, which is better than other detectors. For example, NAITL detectors, which have an energy resolution of only of around 7% at 662 kilo electron volt. HPG detectors work by producing charge carriers. When photons interact with material within the detector, the electric field then sweeps the charge carriers to the P and N electrodes. So the right answer is small size and W. So a small W value is the right answer. Okay, the option number B. Next question. The next question is saying which detector is most suited for high resolution gamma ray spectrometry? High purity germanium, NaITL, plastic scintillator, or LaBr3 with cerium? I'm giving you 3 minutes. You can answer this question in a chat box till 3:50. If you can answer this question, pretty good. Option number 4, you are saying. Here, this is the right answer, which you give in the right in the last question. Money. This is due to the high purity germanium. That is why it is highly suited for high resolution in a spectrometry. Now the next question is saying organic scintillators are ideal for what? Gross alpha counting, alpha spectrometry, gross gamma counting, or gamma spectrometry? Anybody of you know the answer? Anybody of you know the answer? So the right answer is gross alpha counting. Good one. Arangumji give the right answer. Mani said third. Gross gamma counting is not right. Kartika don't know. It's okay. No problem. Go through the lecture. Now the question number 10 is saying role of TL in NaITL is what? To increase the scintillation efficiency, to increase detection efficiency, to decrease scintillation wavelength, or to improve the energy resolution. What is the use of tellurium? Can you tell me the answer? Is it to increase the scintillation efficiency, or is it to increase the detection efficiency, or is it to decrease the scintillation wavelength, or to improve the energy resolution? Okay, the right answer is to increase the scintillation efficiency. How? Let's see it. So what happens? Most widely used scintillator, since this is available in a large size and excellent. Now they are hygroscopic in nature. So in there, if we add the tellurium, the energy resolution becomes 6% and the scintillation efficiency becomes nearly 13%. So when we add the tellurium, it increases the scintillation efficiency. Okay, so that is all. So what did we study? We had a question telling about which process results in the full energy deposition of gamma ray photon in a detector, and the right answer was photoelectric effect. How is it the right answer? What are the other processes taking place? You know it now. Photoelectric effect, Compton scattering, and pair production. What are these? The question number 2 was saying which gives exponential decrease, and the right answer is, first of all, what is the three main form of radioactive emission and what are their penetrating power, and then the gamma rays which is exponentially decreasing with it. Now the third question was saying which of the following gases is used as a field gas in a proportional counter. Now before going to the question, we should know what is proportional counter. So in a gas field detector there are three parts. The second part is ionization chamber and the third part is proportional counter. In a proportional counter we use 90% of argon and 10% of methane. So the right answer for this question was argon with 10% methane, which is the second option. Now question number 4 was saying which detector cannot distinguish between alpha, beta and gamma radiation. The answer was gigamolar counter. Sir has already told it in the class. Go through the lecture. Question number 5 was saying which detector is most suited for X-ray spectroscopy, and the answer was silicon lithium. And why the answer is this, I have told you that this is related to the semiconductor detectors. So in a silicon based detector it is most suited for the X-ray spectroscopy. So what happens when X-ray radiation of low strength falls on a silicon surface? You should know it. Question number 6 was saying semiconductor detectors are operated in a reverse bias mode. And what is forward bias mode? What is reverse bias mode? What are semiconductors? What happens there? How does the electron hole formation takes place? Now we know. So in a reverse biasing, there is small leakage current. So due to this small leakage current, in order to reduce the leakage current, they are generally operated in the reverse bias mode. So you can go through this explanation. So the explanation is saying how do you make a diode? So you take a n-type and a p-type and join them electronically. So when you say n-type material, which means it is rich in electrons, and when we have a p-type material, it is rich in holes or electron deficient material. So when you join them, then depending upon the type of biasing that you invoke, you have different scenario. So this is a two electrode system. N-type and p-type material are there connected to the anode and cathode of the detectors and the biasing system. So when you do a forward biasing, what do you mean by forward biasing? That means the electrons are going across the junction to anode and holes are going across junction to cathode. So when we join the N and p type of semiconductor materials, and if there is a forward biasing, then you will find there is a flow of electron and holes across this junction, and there will be a large amount of current generated even without any radiation falling on the detector system. So this is called forward biasing, and this mechanism results in a large amount of leakage current. That means inherently there is a lot of current flowing through the circuit in which system is in the forward bias mode. So this forward bias mode is not utilized for using this in a radiation detector. On the other hand, let us see the reverse biasing mode. The reverse biasing mode, n-type semiconductor is connected to the anode, so you have the electron going towards anode and you have the electron deficient side connected to the cathode. So what is happening now? When you apply the reverse bias to this diode material, you will find that the electrons are going to anode, the holes are going to cathode, and so there is a no net flow of electron and holes across the junction. That is why they are better for radiation detector. So in a semiconductor, we know electron hole are generating. In a forward biasing, what is happening? There is already a larger leakage current, so we are not able to make a good radiation detector. In a reverse bias mode, there is no leakage current or small leakage current, so they are generally operated in a reverse bias mode. Is it clear? Are you people able to understand what I am trying to say? Arumugam ji, were you able to understand this question? Kartika, did you? Mani, did you? Okay, good. Good. Arumugam ji, what about you? Okay, great. Hmm. Now, in the next question, we discussed that how this SPG detector has excellent energy resolution, and the right answer was a small w value. I will upload the PPT. You can go through it. Then the next question we discussed which detector is most suited for high resolution gamma ray spectrometry, and the right answer was high purity germanium. Okay, next question was organic scintillators are ideal for what? Gross alpha counting, alpha spectrometry, gross gamma counting, or gamma spectrometry. The right answer was gross alpha counting. Go through the lecture, and then the last question was what is the role of TL in NaITL, and the right answer was to increase the scintillation efficiency. So I hope this will. Okay, reverse bias means, okay, let me tell you again. I'm explaining to you. Are you seeing this figure money? So they what happens in a semiconductor? What is happening? Let me explain it from here. So in a semiconductor, what are semiconductors generally? So when a radiation is, you know, getting radiated over semiconductor material, example silicon. So they have a valence band and a conduction band, and there is a band gap. The valence band and the conduction bands are not overlapped, and if the band gap is nearly 1 to 1.5 electron volt, they are semiconductors. Okay, or there could be n type of semiconductor or p type. N type are electron rich, pentavalent, example phosphorus and antimony. P type are electron deficient, they are trivalent, example boron and aluminum. So now let's talk about silicon example here. So when this radiation is falling on silicon, there is electron and hole pair generating, and this hole remains in the valence band, and the conduction band, the electron excited goes to the conduction band. Now this electron is here, this hole is here. Okay, now let's see what is happening in a semiconductor diode. Now forward biasing and reverse biasing means what? What happens in a forward biasing when you are giving a bias? No, n type. N type is already having electron, p type is already having holes. When you are when you are connecting the negative side of the bias to the n type side, to the n type side of the semiconductor, then this is forward biasing. When you are connecting it in a reverse manner, the positive side to the n type and the negative side to the p type, then this is reverse biasing. Now how it leads to the small leakage current? What happens? So in a two electrode system, n type and p type materials, they are connected to the anode and cathode of the detector. Now when do you do forward biasing? What does happen? What do you mean? Electrons are going across the junction to anode, and the holes are going across the junction to cathode. Electrons are going across the junction to anode, and holes are going across the junction to the cathode. Okay, so what is happening when we join the n and p type of semiconductor? If there is a forward biasing, then there is a flow of electron across this junction, and thus there is a large leakage current. Now what happens in the reverse biasing? The n type semiconductor is connected to the anode, so you have the electron going towards the anodes, and you have the electron deficient side connecting to the cathode. So what is happening when you apply the reverse bias to the diode material? You will find that the electrons are going to the anode and the holes are going to the cathode. So there is a no net flow of electrons and holes across the junction. That is why there is a small leakage current, and then the current that will be generated will be due to the X-ray radiation. This in forward biasing, what happens na money? Even when you are not radiating, even you are not putting the radiation onto the material, it already shows you a large amount of current. So you don't know what is the amount of current which is coming due to the X-ray or the gamma ray which you are radiating over the material. So what is the purpose of making a radiation detector if you are not able to detect it in the current form or in the voltage form? So until unless you don't put it in a reverse biasing which has a small or negligible leakage current, you will not be able to find out the values, the numbers of a radiation detector. Okay. Okay, depletion layer. Very good question. What happens when this N and P type material, when we combine N and P type material, na money? So this is electron rich and this is hole rich. So this electron comes here and the holes come here. So this there is a portion of here where there is an intrinsic electric field which generates in the direction from negative to positive. So this is a depletion layer which is forming when you connect the N and P type. But when you are giving bias, the flow is directional. Okay, Money. How do you get the drive files? Just a minute, Kartika. I am just showing you. There is this no. Uh, Many people are already there, no? Okay, let me get a shareable link for you and put it here. This is there. So you know this drive has three folders. Okay, sorry, this is the link of spreadsheet. The drive is there. Just a minute. Folders. Yeah, here it is. So if you go through this spreadsheet, no, there's already a presentation folder link. You all can access it. So in this presentation folder link, when you will open this link, you will come to the drive, which has all the details like week 1, week 2, week 3. Suppose I am going to the week 1. So in the week 1 classes, I gave you a PDF for help, then a combined lecture PDF, the presentation and the recording of the class. If you're not able to follow the YouTube channel, you can go to the recording of the class. You can see the combined lecture here. Example, week 1 combined lectures are here. So whatever in the first week Professor Tomer has taught from what is radioactivity and different kind of radiation, they are here. And then there is a PDF for help here in the week 1 example. So similarly, there is this presentation which I do, which contains the answers of the assignment, and then there is a recording. Similarly, for other weeks are there week 2 presentation 2 and class 2 recording, and then there is week 3 which has full PDF, class 3 presentation and class 3 recording. Similarly, today what I will do now, okay, good, Money, I'll explain you. So Money, it will be better if you unmute. If you are not able to understand, you can discuss with me. So Kartika, so I am saying something to you. So I will upload today this interaction radiation thing and this merge PDF and my PPT, this PPT of 10 questions, 29 slides, and the recording of today in this drive. Along with that, you will have it on my YouTube channel. The link of the YouTube channel is this. So all these are uploaded in this spreadsheet. So if you open this spreadsheet now, you will get everything. You will get everything. So you just save this spreadsheet link, which is already shared with you, I guess, by the NPTEL people, but still. Okay, Money. So you tell me, what do you want to know? You are studying in Central University of Gujarat. So you are doing bachelor's or master's? And MSc. MSc in what? Chemistry or some specific branch of chemistry? Like organic, inorganic, physical. What is the specialization? Or it is general chemistry? Oh, you are MSc in industrial chemistry. Let me tell you, I am BSc from industrial chemistry. Okay, great. So did you do BSc in industrial chemistry? Bachelor's also in industrial chemistry. Okay, so why did you choose industrial chemistry for masters? I mean, let's have a discussion today. Then I can tell you other things. You don't means? I mean, you chose industrial chemistry, no, for getting admission, or you were not able to get other courses. That's why you had to choose industrial chemistry. I mean, did you choose it on purpose to get a job? Okay, no problem. So let me tell you, I am a bachelor's from industrial chemistry from Delhi University. That is why I was interested to know that. So let me tell you what happens. PMRF is a Prime Minister Research Fellowship. It is given to the scholars which are doing good research nationwide every year. So it happens 2 times in a year, similar to the net exam, which happens in June and December. This happens in May and November. May or no, May cycle and November cycle are there. So till now 10 cycles have been completed. So what happens? There are two channels. One channel is a direct channel and one channel is a lateral channel. In a direct channel, what happens, Money? If you have not got admission into PhD, what you do, you must have done some project before, some internship, something. So if you have published some paper, you're net qualified, you're gate qualified, your rank is fine, your recommendation is strong, and if you are joining a lab where you are going to work in the same field where you have got some publication if possible, which is difficult to get at a master's level, or you have a proposal which is very strong, then you can ask your PI who is going to take you for PhD to nominate you for a direct entry channel. Now they are generally in the central universities or Indian institutes. Okay, so generally direct entry channel is very difficult because there are very few people who have good rank along with that all this by MSc level. Now suppose you have joined the PhD. Now within 1 year of PhD, if you can get some paper, some publication, even a co-author publication. Along with that, you have to maintain a good CGPA, which is master in CGPA and master for direct entry also. The CGPA should be 8.5 above. Okay, so if you have CGPA more than 8.5, if you have certain papers, you have a strong recommendation, you have a good proposal, and if your PI is willing, so your PI will nominate you, and among these nomination, depending on the people allotted to your institute for PMRF, you will be get selected. Now every year there will be a review. Every quarterly you have to update the website. How many papers have you published, how many patent do you have, like this TA ship I am doing, you have to do certain TA ship, and etc etc. So you have to, like, you need to perform better than the normal, the other researchers, because you are getting quite handsome amount of money than them. If you need some more information, Money, you can call me or you can message me on this number. You can see this is my email ID, sg19ip011 at the rate isaacole.ac.in. And if you have any doubt regarding the course, you can mail to me, and the mobile number is 7355013861. Okay, so you can write to me and I can explain you in detail what is the purpose and how does it happens. Okay, and you're interested in material sciences, so yeah, I would suggest you do some internships. You're in which year, by the way? Money, are you there? Money, you're in which year? First year, second year? Okay, no problem. You note down my number. You're in which year? First year or second year? Okay, great. You do some internships. I suggest you do some internships, and if you can publish some paper, and you join the same lab where you're doing the internship. Like I'm telling you a channel, how do you get a direct entry, and then you ask your guide to nominate you. Or you can do one more thing. What you can do, you can join as a project student in an institute. You can work for 1.5 year, and then you can publish some paper and then join the same lab for PhD. All it is wasting your time, but then you have probability of getting PMRF. Okay, if you have publication, a strong recommendation, then you have more chances. So it depends on you. You are going for a direct channel and lateral channel. Mostly out of 10, 8 are from 8 or 9 are from lateral channel. One is direct channel, because hardly anybody has so much exposure of research at a master's level. Okay, so you note down my number. I'm giving you in the chat box also. If you have any query, you can write to me or you can call me. You can WhatsApp me. Okay, is it okay, Money? Okay, no problem. So Anumugam ji, were you able to understand what was discussed in today's class?
Yes, sir. I understand. Thank you, sir. Thank you for valuable solving.
Okay, Kartika, were you able to understand? You can write in the chat box. Okay, great. So I think this is okay. Thank you, Mani. This is all for today. If you have any query, you can write to me, and then let's meet next week. So see you. Take care. Bye bye. Okay. Bye. Thank you.